in the chat. So perhaps just interrupt, because I can at most do one thing at a time, and that doesn't include reading chat and clicking on too many things. So please just interrupt me if you have a question or if the moderator sees someone asking something. Good. So first of all, let's start at the basics, the why of modeling. In the real world, we are very often faced with problems. And those problems can't be solved by trying different solutions. And if the solution doesn't work, just to try something else. The reason is either time or practicality and money. You can't build a new freeway network just to see if that's going to be better than the existing one. Or you can't rearrange the conveyor network in a warehouse to see if that will increase productivity. Therefore, what we have to do is we have to move to the world of models, from the concrete to the abstract. And we have to look at the real world problem, and we have to decide what assumptions are we going to make, how are we going to build a mathematical or a simulation or other model of the real world so that we can then solve it. And that solution can either be an analytical solution or simulation solution. And if that solution was good, then that will tell us what to do in the real world. And the other thing to bear in mind is this is very often not a single iteration process, that very often we go through this a few times because the model doesn't quite, or the solution doesn't quite fit. There's something that we've left out, and we have to go through this a few times. But the good aspect of this is that everything in the world of models is really in the risk-free space environment. So we can try what-if analysis, a whole bunch of things that we cannot do in the real life. And this is really why we do modeling. And the most common modeling tool is Excel. All companies use it and sometimes abuse it because Excel's strength is that it takes certain inputs and then creates some outputs. And there's an analytics engine behind it consisting of some macros or formulas or scripts that would do these calculations for us. And that works well for many cases. But for some cases, it might not be the most optimum way of doing it. Now let's look at something that sounds quite simple, and that is to move a product from between two places. Let's call it A and B, and they geographically separated. So it takes a certain time to move the product, from A to B, but there's always some uncertainty involved in delivery times. Maybe there's some breakdowns that occur. And then once the product arrives at B, there might be other causality that it triggers another process. And then there's quite often a large number of projects in our supply chains. How should we ship? Shall we own a fleet or rent the fleet? And when is the optimum time to ship? And which sort of route should I use to supply the raw materials and so on? And then at the same time, there's also an interaction with other processes that happen behind the scene, things like sales that might be driving this whole supply chain or other manufacturing processes. And this is sort of what I'll show you a little bit later in the example model, because all these aspects is in there. And to do something like this with a tool like Excel is a little bit challenging because there might be many feedback loops, a lot of uncertainty, stochastic behavior, and it cannot always be solved just with a easy underlying algebraic equation. So this is where simulation modeling come in? Because we look at which are the input parameters and what KPIs do we want out of our model. And then sort of the magic happens in the actual building of the model that would describe the system's behavior. And when we talk about the system's behavior, when we run the model, it's a continuous process and there are different trajectories. So there's not just one output, there's, depending on different things happening within the system, there can be different outputs over time. So we want to run this multiple times to get a good understanding of the whole system. And the kind of outputs that we get from simulation modeling is much richer than a tool like Excel, because we can measure the outputs and get distribution functions of that. Let me just hide my window completely. And very importantly, we can also animate the system behavior. And this is especially useful because if you have a model, you can fault find, debug the model, see when things are not quite the way you expect it by just looking at how the visual story unfolds. And this is also something that you can share with some subject experts on the factory floor, or your simulation chain experts, and they can quickly tell you what might be unusual about your model. And do what-if experiments, compare scenarios, looking at risk, and then look at optimization, which we'll also cover a little bit later today. So you get this very rich output, which very often spreadsheet-based analytics can't give, or even linear programming tools cannot always give you. Very often also in real life, there's all kinds of heuristics that should be part of a model. So for instance, normally the transport would deliver goods to a particular manufacturing site, but at other stages, they might, when they're empty, go via another route to pick up other raw material and take it to other factories. So that's not something that always happens, but just on occasion. And very often it's rather difficult to build these exceptions into a linear programming or nonlinear model, whereas with simulation modeling, you can really model the system as it really happens in practice. Then the kind of application areas that exist for simulation model would range from the physical level, from the factory floor where people are walking, or where forklifts might be driving, to small sites, to rail yards, traffic, supply chains, delivering between warehouses and distribution centers, and then even on a strategic level, where we might look at product portfolios, the change of raw materials, commodity prices, and so forth. So it ranges from the low abstraction level, where there's a maximum amount of detail how things sort of really are, to high abstraction levels where there's very little details. It's sort of more the big picture change in the economic environment, to the medium level. And there are different modeling paradigms that's been traditionally applied to these. Discrete event, look at the sort of bottom to middle level. System dynamics, typically more at the higher abstraction level, and agent-based modeling can be used for the whole range of these products. And then specifically looking at simulation transportation, low abstraction level, as I said, pedestrian flow, rail yard transportation here in medium, sea, rail, and so on. And then more the social dynamics, market competition at the higher level. And then just a brief foray into where these come from and how long they've been around. System dynamics have been around since the 50s, where we look at stocks and flows and changing a particular stock into another one by a flow being controlled with feedback loops. Process-centric or discrete event modeling, where we provide a particular flow of entities through a flowchart-like environment. And then agent-based modeling, where we don't have that, but we have individual agents that would interact with each other, and they would also have a particular process that they go through. They can manufacture other agents or interact and create more agents, and they can also interact with the environment. So typically with these, we let the agents interact and then see what is the resulting patterns that may emerge. And when we talk about agents, we not only mean people, but we can also mean equipment, non-material things, and even organizations. So it's a very flexible paradigm. And why we like to use AnyLogic with our consulting hat is it supports all of these, and we can switch between different methods and paradigms within one model. And I'll show you two good examples where we actually do that very briefly. And because it's an object-oriented platform, we can reuse these elements that we then develop. And there's a whole range of companies that use AnyLogic. In many different sectors. And what is always amazing to me is that one product can have so many applications. So it's a truly general modeling tool that can be adapted, to your particular needs. So now let me look at a slightly more practical application. And that is, if we have certain logistics or business or mining operations, very often discrete event modeling or process-centric modeling is the obvious choice, because we have different entities that's being assembled, that's being manufactured. There's some queuing and buffering taking place. So discrete event modeling is good to model those. But then sometimes you have to develop a larger model where you don't just manufacture things. You might want to see how the goods, the raw material arrive within that facility and how it's dispatched to other facilities. And this is where agent-based modeling comes in, because we can use these manufacturing or distribution sites themselves as agents. We can use the transports as agents. And there isn't always a predefined route, because we might ship to those particular warehouses that need our products as and when they do, and the decision making may rest with the vehicle, for instance. And then we can add the other component, the system dynamics component, to this sort of view, and maybe drive the supply chain with our consumers, where there's certain changes in behavior, maybe demographics, places where they might be located, that will then change our supply chain. So we can do this whole process of a large supply chain using the different modeling paradigms. And it's not just in supply chain, we can use it for, healthcare, marketing, passenger terminals, and a whole range of other industries. Now, how we build an AnyLogic model is we, as the programmer or coder, can just drag and drop elements from domain-specific libraries, and we can also adhere to the different paradigms by building it in a discrete system dynamics or agent-based way. And we can also extend it with Java programming language, and then eventually, if required, run optimization experiments on that. And practically, when we develop a model, well, sometimes even simple models, as I'll show you just now, but definitely larger models, we cannot drag and drop things because you have too many distribution centers or customers. So AnyLogic allows us to configure a model from a database. So the database would contain where and how many of the different agents we have, and that will then be placed on the map itself. So now let me move across to AnyLogic. So as I've just said, this model is, well, I said models can be constructed, and this specific model that looks at product delivery is constructed from the built-in database. So we have certain manufacturing centers, in this case only 3 of them, and I just stuck with the USA ones, and then about 15 distributors. So we just use the names of these, and behind the scenes, AnyLogic will look it up in OpenStreetMap and find the GPS coordinates for these, but we can also specify them explicitly. And the nice thing is we can delete some of these cities, we can add new cities, and the model will automatically configure itself. If we look at the model itself, and maybe it is a good idea to run the model. And it is that one. And what I will do is to start off very slow. So let me just start and stop the model. So hopefully you saw some yellow envelopes flying from different manufacturing or distributors to the manufacturing centers. So we have 3 different manufacturing centers, and then we have a range of distributors placed geographically. And how the model works is each of these generate an order at a random event, and I can click and have a look at it. So it generates an order, generates a demand, and then would send that order to the closest manufacturing facility. And that manufacturing facility, if I dig into that, would contain some discrete event logic, process-centric, where it puts the orders in a queue. It would then see if it has enough inventory to fulfill it. If it does, it would then take a vehicle, one of the vehicles stationed there, and then do the delivery. And what is quite interesting, we also have a system dynamics component where the production rate is creating inventory, and depending on that inventory, you would fulfill the orders from there. And then we would also be doing cost tracking. So there's a certain cost associated with the vehicles. In this case, we have 3 vehicles, and we can change it by moving the slider around. And then there's a certain cost for operating the facility, for producing things, and then if the order isn't completed in time, there's a penalty cost involved. And the important point here is we can customize this to the particular situation. So we can choose how much detail to add, and this is a sort of a relatively simple but quite elegant model that looks at all of this. So if I carry on running, what you would see is, for instance, here, there's 1,460 items outstanding that has been placed. The order has been placed. Maybe I should speed it up a little bit. And now you see the truck is coming with that particular order, which would now fulfill it, and there's no more there. In the meantime, randomly, another order will be placed. The time between orders is random. So in this case, that order is being fulfilled, but the next order is close to being placed. And the moment it runs down to 0, you'd see the order is being placed. So if we look at that one, nearly, and now they'll place the order. The order will go into the queue, and the transport is quite efficient from there. So we can then look at the statistics to see what products are manufactured at which centers. We can see, for instance, the utilization, the mean waiting time by looking at this histogram and looking at statistics for, I don't know, product cost over the 3 days and order duration over 3 days, and how these orders are being placed. So what one can do is to get an idea of what happens to your supply chain by switching certain of these warehouses on and off. We can change the production rate too, and let's perhaps just try that. So now let's say we're going to switch that off, and we're going to decrease the number of vehicles and then run through the 30-day period. We can then see what the how long the orders took, and you will see these Pittsburgh and Nashville disappeared earlier, where Chicago was the one that carried on operating during the time. So we can sort of do these what if analysis by just playing around and getting an idea of how the dynamics by changing the production rate in the vehicles. But as you can imagine, as you have more parameters in each of these, it will become more and more difficult, and that's why we would run a simulation experiment. But before I show that to you, let me just quickly dig into the details a little bit more. So in this particular model, we have a number of agents. I've already shown you the distributor agent and the manufacturing agent. We also have orders, which is another agent, which is the way they communicate, but we also have vehicles. And if we look at the vehicle, we can model that to arbitrary amount of detail. In this case, we used a state chart to model the operation of a vehicle. It would be normally at the manufacturing center, and then once it receives an order, it would start loading. After some time, it would move to the distributor, and so on and so on. And by the way, these are typically stochastic values that we enter here, or we could have maybe historical data that we run through this model. And so we can really build the logic and heuristics that exists within the operation into, for instance, the delivery fleet. Now, what we want to do is we can choose various types of optimization or various types of experiments, and one of these is optimization experiment. So if we choose that, we can say we want to minimize the mean cost per product, for instance. We can say a certain number of these parameters would be fixed, but others maybe would be varied between, they would be, for instance, between 1 and 3 vehicles at each of these sites. The production rates might vary, by a certain step size between that, and we can then leave it to the optimization engine to find the optimum value for these. So at the bottom, you can see this is running on a number of different processors, and it starts with a particular value, 61. The best one it's found is 35, and from there it will see if it converge or improve. So it's using the OptQuest engine, and this engine is used in many simulation products, and it uses different heuristic genetic algorithms and so on to do these optimizations. So I'm not going to wait for this to finish, but you get the idea. It would then find um, the best solution so far uh, to minimize uh, the delivery. And obviously, there are different ways of running this. That if it's a stochastic demand at the various places, we would run the model many times to be able to get a good answer where our warehouses should be uh, and what the number of vehicles should be. For instance, in this case, I didn't add the warehouses to be closed or not, but that is obviously something that you would do if that's important for this particular model. And now another model that is in a way similar, but in another way completely different from this is a reverse supply chain model uh, that I developed for finished client. And this model, instead of, okay, let me just stop this. Well, this can carry on. So in this case, the trucks are not situated at the central location, but the trucks or transport are situated at the various sources of products that's being moved to a bioreactor. And these different products or sources are different waste sources. So it would contain animal manure, or it would contain plant or industrial waste. And if I, for instance, look at this one, I would then see it's a farm, it's a vegetable farm, and a certain amount of waste material is produced. And once again, I've used a system dynamics model or element to illustrate the waste material. Sometimes it's consumed on the farm or on neighboring farms, and then the material has a certain nutrient content, the waste material, and that would then be transformed or transported rather to the bioreactor, where at the moment you would see, well, these are the quantities of incoming waste, all the combined garden waste, industry waste, and so on. And this is the total storage of the feeds on premises in a buffer, and then it goes through the biodigester, and it's being converted into useful energy and concentrate, which can be sold as a source of revenue. What is quite interesting about this model is the actual calculations of how this waste is converted into useful products is an Excel model that was developed by the researchers. And AnyLogic sends information every time a load arrives. It would send the information to Excel. Excel would do the calculations and tell AnyLogic, well, this is the waste break or the valuable products that's produced from here, and it would then save that information. So we have AnyLogic running at or Excel running in the background doing these calculations. So one can have these black box components connected to your model if that is desired. And then finally, we can look at the statistics, and the statistics would then sort of show you the volume of that's stored at the reactor, and one can then run optimization experiments to see, well, how many of these do I really need, and which combination of them to supply a continuous amount of waste material, but not so much that there's not enough storage available. Good. And then what I want to do is to move on to talk about combining simulation and AI. So this is, in a way, a very well, a recent uh, development. Last couple of years, AnyLogic has been very active in this field, and I'll be looking at three benefits specifically: generating synthetic data, using it as a test bed, and then for a learning environment. So first of all, synthetic data generation. So we can create simulation models of a particular operation, which would then generate large amounts, as much as you really want, uh, data that's clean and relevant and structured and even labeled to then train your neural networks on. Because sometimes if we just look at historical data, we might not have enough of that data. The data might be very messy. It might be very time consuming to label it correctly. So the other benefit is we can really capture the behavior of a system by building a digital twin of that system. And then the information in the data, the synthetic data that we get from this, isn't just historical data. It might be certain events that haven't been captured in the historical record, uh, and therefore it might be more valuable to train it on these, because, as I said, it can uncover certain scenarios that just hasn't happened yet. So that's a few of the reasons why simulation works very nicely as just generating synthetic data, which will be sent to AI just to train that. But after the AI has been trained, we can also use the simulation as a test bed for that, because the AI might have been trained, but now you want to put that back, plug that back into your digital twin of your operation to see, has it really improved things? The AI might have improved one particular component, but the question is, how would that now affect the whole system? Perhaps now the bottleneck is just moving to a different operation, sorry. And it's very effective for doing that. And then finally, what we can do is we can use the simulation model itself to train the AI, specifically reinforcement learning. Because with reinforcement learning, AI is really playing with the environment, and then as things develop, it gets rewards, or it's punished if there isn't if you don't have the desired outcome. And from those interactions, it learns. And by doing this, it can really speed things up because it's in a virtual environment. It's also a safe environment because there's no chance that the AI can crash a robot arm against something. You can train it in this virtual environment where it would know the sensor outputs, for instance, and then from there learn how to most efficiently move between 2 points, for instance. So, and this brings me to one of the examples. So, AnyLogic integrates with a number of different AI uh, products and vendors, and I want to show you one of these, and it's from Microsoft, and it's called the Bonsai Network. And how it works is there's just as we ran those simulation experiments, optimization experiments within AnyLogic, there's also a reinforcement learning experiment possible. And after setting that up, we will then connect to the Bonsai that's hosted in the cloud. And we would then train it. And after training it, we can deploy the brain to run our model. So let me quickly show you what it looks like. Now, this sometimes takes a few seconds. Good. So if you look here, there's only one uploaded product. So what I'm going to do now is I'm going to start AnyLogic. And I have to just change one of the parameters here. So if it's set to 0, it knows it's training, and previously I just ran the original simulation for you. So it's just a little switch. So now if I run my AnyLogic model again, so this is now going to be a training simulation. So I start this and start playing, and AnyLogic is now running on my computer here. And when I press run, it will try to connect to the Bonsai server in the cloud, and it's just managed to do that. And if I now have a look here, you can see it says here unmanaged simulator is connected to it. So this is my simulator that's actually on my computer. And what I want to do now is to try to show you how I would train that. So let me perhaps just very briefly jump back to AnyLogic. So within AnyLogic, I have an experiment, not just the optimization one, but also a reinforcement learning experiment. And there, just as an optimization experiment, if you remember, there were certain parameters that were fixed, other parameters that I varied. In the reinforcement learning experiment, there is something similar where I would observe certain variables, and then I would add code that would tell me what the desirable outcomes are that I would be looking for. If it doesn't manage to do that, it would give it a particular penalty, as you saw in the manufacturing center. And I would then press training here, and I would go to my unmanaged simulator, which is now on my machine, and it just takes a few minutes to connect to that. And then it will start the run. And what you will see, hopefully, is the brain will then tell the AnyLogic to start running, and then it will vary the parameters, and then it will observe the outcome, and then it will repeat that process. And if the results are worse than before, it will try other combinations and permutations until it begins to find settings that give it better values, and then based on those better values, it would explore further. There we go. So it's running. So as you can see, my simulation model is now controlled from within the cloud where this model is situated, or where the brain is being trained, and it will now learn which settings would give me the best outcome or the desirable outcome. One of the big benefits of using AI reinforcement learning is, whereas when you look at OptQuest, you typically have one function that you're trying to either minimize or maximize, where here is you can explore a whole range of different outcomes that might be desirable for you. But this is obviously not the most efficient way of doing it. A better way is, now that you're sure that your simulation model really works, is that you then upload that simulation model, that AnyLogic model, into the cloud. And now you would train it using the uploaded model. So it now no longer have to run it on your individual machine somewhere, far away from the US or wherever their server is. It can now upload your model and run it over very many multiple processors in the cloud, and it's obviously much faster. And within a second or so, we should see the output of my previous training, which took about nearly 3 hours. And then what one would typically do is you would then export the brain, and then you would run your AnyLogic model, or your model for your particular real world problem, and the model would then be controlled by the exported brain. So it would know what those particular settings are. If you change a particular setting, it would know how to change the others to give you the desired outcome. Okay, so maybe while this is just connecting, I see I only have 2 more minutes left on my 45 minutes. So let me perhaps ask if there's any questions.
Hi, Clemens, thanks. We do have one question from Stuart. Could you give us a sense as to the number of agent instances you might be able to run in a simulation, and the performance, sort of rate of messaging between agents that can be sustained in a simulation run?
That is quite a difficult question, because it depends on the amount of complexity in the agent itself. But we've run models with hundreds of thousands of agents. That's a very sort of hand-waving answer, but it really depends on what the details of the agents are. When you do agent-based modeling, you don't necessarily have to have one agent per whatever you looking at. I sort of skimmed over that a little bit. So if you want to model the population of, for instance, South Africa, you don't have to have 60 million agents. You would make certain assumptions. You would either put, say, one agent equal so many people of these kind of demographics, or you would make the environment smaller and saying, instead of modeling the whole of South Africa, we'll model this area, which is sort of like a microcosm of that. So there are different tricks you can perform if your agents are quite complex, but you need to run a practical model.
Right, thanks, Clemens. I suppose maybe a tying question then is, you mentioned the AnyLogic could represent these different levels of abstraction, from using a system dynamics approach down to a discrete event simulation. Are you able to link those models up, or are they necessarily separate models, or are you able to let one model inform another model as you drop down through that sort of abstraction layer? Is that possible?
Well, the model I showed you actually mix those up. So it's not as if you have different models doing different things. Within the, for instance, truck agent, you can have some system dynamics calculating the CO2 or the carbon footprint of that truck as it drives. So you can mix these methods within one model, but you could actually have different models that you maybe link, because maybe the one model is looking at the environment, I don't know, consumer behavior, and the other model looks at manufacturing or recycling or whatever, and you can then link these models together if that is what you want to do. So it's a very flexible.
Right. Okay. Nice. I've got a question from Krista. For the simulation optimization with OptQuest, is there an option to see or select which optimization algorithm is used, or to compare the outcome of different optimization algorithms?
That's a very good question. So OptQuest is a third-party tool that's sub-licensed by AnyLogic. So you have to check on that if there is ways of telling it do that. Within the sort of general AnyLogic environment, I don't normally do that. I just let it find a good solution. But there might be some settings where you can indeed do that or compare different methods. But sort of looking at a broader perspective, what one could do is you don't necessarily have to use OptQuest. As I've just shown, you can link to AI. There is a movement in AnyLogic to incorporate Python within AnyLogic. So you can have different AI that you want to train, or even different linear programming or other optimization that might be implemented in Python or Java or some other language. And you can then link that to AnyLogic as well. So you're not necessarily stuck with, okay, we have to use OptQuest.
Great, thanks, Clemens. I always feel that the simulation domains always have such nice, they're so visually appealing that they immediately have a leg up on some of the more mathematical approaches, because especially when you're trying to explain to clients. I mean, is that something that you found in your career with simulation, that people are more sort of open to being more confident in solutions when they see simulations versus just an output?
Yes, I see this as one of the big benefits of simulation modeling. And this is what I sort of hinted at the beginning too, that is the why of simulation modeling. Why are you building this particular model? Sometimes it is to really create a digital twin that no one will really see. It will be hidden behind, in some kind of server room, just being pulled and making decisions, and no one see it. But there are other kind of models that you might build that's at a higher level of, or that's not at such a level of detail, but you want to explain a particular concept very often to stakeholders. And that's very important, because once people can sort of see how you can tell a story with a simulation, and they can visually verify to some extent to themselves, yes, this is really what happens. Because as a consultant or professional, your job is really to enable people to make better decisions. You can build the best model in the world, but if the client doesn't implement it or don't believe you, then it's not really worth that much. You have to have a way of convincing them, or allowing them to convince themselves, by maybe deploying the model to the cloud and giving it to them to drag things around to run their own data through that it's a useful model.
Right. Yeah, I see that a lot in what we do. I mean, and I think that, as you said in your talk, I mean, there's so much power in combining these approaches, because we do a lot of our work in sort of the MIP space, where we're doing a very fast search through a large amount of options to find feasible or optimal solutions. But I think the ability to then show that solution as a simulation, and then to be able to test the robustness of that solution by experimentally changing some parameters in the environment that aren't in your actual model to start with. I mean, these feel like very powerful ways of combining these approaches.
Yes,
So
and indeed, and it might be that the AI found, really brought a particular parameter KPI down and really improved it. So that's fine, but maybe you only tested it for one subsection. And once you then put that back in your whole organization, it might cause other unforeseen effects which you didn't anticipate.
yeah, right, exactly. You have the best saying of the talk I've seen so far, and that is an exported brain.
Well, that's one of the Microsoft technologies. I guess they came up with that. Their marketing department.
No, it's very cool.
Yeah.
How
So,
is your
sorry.
how is your run doing? Are you waiting, or are you finished, Clemens?
I have. Okay. Well, I probably clicked on the wrong thing, but let me just quickly share my screen. Wait, before I share my screen, let me just. So, any other questions while I quickly grab this? There we go. Okay, so as a plan B, because I know these things don't always play along, I did have a screen capture of this before, so it's now running in the background, but it's not really what I wanted to show. But I just wanted to show you that particular image of what the trained simulation looked like. This one. So at that stage, it was 17 hours. So it would try different iterations and different values. And it's currently finished, but I haven't actually exported it and run the simulator. From there, I just sort of stopped here. But you can download the white paper. There's a number of webinars involved, not only for Bonsai, but also for some of the other reinforcement and AI providers that AnyLogic is collaborating with. Good.
Very
Thanks a
interesting.
lot.
Thanks, Clemens. Yeah, are there any other questions, or do people have any follow-up questions based on what we've spoken about? You can just unmute yourself and ask the question.
I'm always curious when it comes to building these sorts of models. How long does it normally take you for a client to, I mean, obviously it depends on the kind of model, I realize that, but just to kind of get a sense of the effort and complexity involved.
It depends. I can't really, I don't know, from a week to 6 months or a year.
Okay. Yeah,
It really depends, and very often the development of the model, or the majority of the time, isn't necessarily spent sitting behind the computer coding things, but is to understand exactly what should be modeled, is to have meetings with the client, is to show what you have. And very often it's also the client asks for something, and then halfway through they realize, no, that's not really what they want, or things are different, and it's sort of a change. So it's I guess like any kind of consulting job, where the trick is to find out what the real question is, and then to build it in such a way that that is adaptable enough to be changed throughout the process.
Yeah, and I guess part of the process is it's exactly that in terms of the you almost want the client to realize that maybe they didn't understand their problem in the first place. So it's kind of a good sign when they start engaging and needing to adapt. But obviously that then protracts the engagement, and if they weren't expecting that, then that kind of can make the consulting engagement difficult.
Yeah, and a good way, what we normally try to do is to have a phased approach. To instead of saying, sort of as I guess a number of years ago people did, well, give me the whole spec of what you need, which in itself took months and months and months. And then if you then follow that spec, it will be very expensive. In the end, you deliver something and the client realize, well, that's not what they wanted. So what we tend to do is to rather have sort of short sprints, short phased projects where we say, okay, first we just want to do this. And does that look right? Okay, now we adopt it and add more complexity and more complexity. That's much better because then you sort of discover what you need to do along the way.
Yeah, absolutely.
Yeah, and I think, sorry, I think just building on that point, I mean, as someone who comes from a very sort of software background, I mean, to me, a big challenge would be understanding whether the simulation is correct and that you haven't introduced any sort of unnecessary bugs that that must be a challenge.
Yes, you need to obviously validate and verify the model, but even having done that, it's very important in the beginning to try to find out what is the real business case that I'm trying to model. Because that would depend what you have to do, and then to always follow the sort of rule of thumb to rather do something as simple as possible, or as simple as it need to be, or only as complex as it need to be, rather than to jump in and add all the bells and whistles. Because, as you know, the more code and more lines of code you have, the higher the probability that there's something in there that might have a bug.
Right. You mentioned digital twins as well. I mean, that seems to become sort of, you see that a lot more in the press recently, this idea of digital twins. Has that sort of raised the interest in systems like AnyLogic and simulation in general? Have you seen that?
Yes, it has. But and digital twins are quite often, sort of different buzzwords. And very often people just really mean a simulation model with that, rather than a very accurate digital twin of their facility. But some of our clients are using it as a digital twin where they have instruments on the factory floor feeding into the simulation as well. So it's a true digital twin. It's not just sort of a low detail approximation of what they need to do. But once again, it's what do you really need to build? What is the reason that you need this? So you don't always have to go to that level of detail.
Right.
And out of curiosity, in terms of the digital twins, I mean, if you're gathering that information, are you reacting to that in real time in terms of providing alternative changes that need to be pushed back into their systems, or are you just collecting that data for later analysis?
Yeah. So what some of the clients are doing is they are running where they would have, for instance, a warehouse management system. They would then create a simulation model, and they would then be running testing out these different bits of equipment with that, where it would pretend that there's certain stock coming in and have to be moved to different places just to see how those things work. So that is one of the applications that you can use this for. But it can be used for planning. So the simulation model is running, but it's being fed with real-time data or near real-time data. and then when things break down, you can see what interventions are possible and how long it might take for the system to get back online again. But there are various ways of doing things. You don't necessarily have to do that, because maybe you have a central database where flags would be set when certain systems go down, and your AnyLogic can read from this database and then advise you what to do. But there are very many options available.
Yeah, great. Thanks, Clemens. I mean, it was a great presentation. Thanks for your time and the presentation. I'll hang around here for another 5 minutes if anyone on the school wants to chat with either me or Clemens. But otherwise, thanks everyone for attending. It was great seeing you guys, or at least seeing your names. Yeah, thanks all.
Thanks a lot.
Yeah, thanks, Clemens. Like I say, I mean, I think the ability to just show those visuals in the simulation world. I mean, it's so much more friendly than seeing pages and pages of inequalities, right? And you just like fall asleep after the first 5 minutes. But the simulations are just very engaging. I must say, I think it's a very powerful tool.
Because I've also done sort of cost optimization models with linear programming tools. And as you say, you sort of get these pages and pages of sometimes Excel, and you sort of then maybe highlight it when, certain constraints are not being met. But then, okay, this is this, and where is it coming from? And you have to jump from sheet to sheet to try to figure things out. Whereas if you can see the what really happens, you can immediately highlight, okay, that little truck has gone red or something, and you can know what happens. And that's the other thing, is when you develop, I guess, any solution, is the maintainability of that solution and how you can deploy it to the end user so they can gain most from that. You don't want something that's very unfriendly or very difficult to comprehend for the end user, because then in the end they just won't use that.
Yeah. Yeah, exactly.
It's also horribly easy for your Excel not to be doing exactly what you thought it was doing.
Yeah, and it's even harder to catch in Excel, eh?
Right.
Yeah, no, exactly.
Do you have any good tips and tricks for how you go about verifying your models? Obviously, validation is going back and talking to the business and checking that it matched what the intent was. But sometimes those models can be quite tricky if you've got a lot of moving parts to check that they're doing what you expected.
Well, one of the things that you can try is to run some historic data through there, where the system behaved in a particular way, and you can get this historical data from wherever, and just run it through and see does it more or less correspond. The other reality is that very often, especially when humans are concerned, there's certain cycle times that management is insisting that this is how long people take to do these things, but in practice that is not always the case, and sometimes the sort of simulation models point these discrepancies out to highlight it. So I would say look at historical data, and then you can also I guess test it with certain scenarios where okay, that and that should cause this problem. Does that happen? Does it behave the way I expect it to? And if it doesn't, does that mean that there's a bug, or is there maybe a new insight that we can get from there? So just developing the simulation model and say, okay, here's the simulation model. I'm pretty sure I haven't made a mistake. It's running. I'm pretty sure it corresponds to your physical layout or your real life problem. That isn't necessarily the end of it. That's in a way the beginning of it, because now you're going to make business decisions. You're going to explore. You're going to get the value from there.
Yeah.
Yeah. Nice. How much is an AnyLogic license these days, Clemens?
I am very bad with numbers, but it's 300,000 plus.
Are we talking rands? Or
Rands, yeah.
right.
Yeah.
Okay.
So it's in that region. It's the big thing is really return on investment, right?
Sure. Yeah.
What are you using it for? If you can save 10%, what is that versus the tool? And the other thing is the cost of the tool isn't really that. Often people ask us, well, can you do a proof of concept model for us for so many weeks? And then we tell them, well, that will be more than the software.
Yeah.
So it's that is just the tool to be able to do this and for you to be productive. But it also gives you there are two aspects to it. The one is how do you need a tool to develop the model, and that would typically be your technical team, your industrial engineers, your subject experts. But then you want to deploy that model to the decision makers. To maybe the people on the factory floor, and how do you do that? So AnyLogic also allows you to do that via the cloud or standalone licenses and so on. Right. So in the end, you have to look at the whole picture and what would you really be getting?
Yeah, for sure. Yeah, no, it's very powerful tool. So nice tool set. But, yeah, well. That was super. I enjoyed that.
Good.
Yes, indeed. Thanks very much.
Yeah.
Okay, and Dave, you well?
I'm hanging in, thanks.
When you're fixing some aircraft,
we're still doing that. Yeah, well, trying anyway. Still working on it. Yeah. You keeping okay?
Yes.
Sorry, David.
Is that a real aircraft you're talking about?
Yes, it's a Spitfire, which until April 2000 flew at air shows. And at the air show in April 2000, it stopped flying. And we're looking to raise rather a lot of money so that we can get it back into, hopefully, airworthy condition again.
Right.
We have a long way to go. Yes.
Nice.
So if anybody feels like turning up at Swartkops Air Base on the first Saturday of any month, I can take you and show you the bits.
Oh yeah, I'll definitely take you up on that. First Saturday, you say?
Work is still
yeah. So a week on Saturday we'll be there again. Yeah.
The 4th of June.
That's right.
Okay.
Yeah.
I must be in contact with you then. I'm sure the kids would also enjoy seeing it. Yeah.
I'd be delighted, yeah.
Oh, thanks.
Maybe you can make it a special Orsa event.
Yeah, I've said that to Dave before.
Right.
And also social.
Yes.
That's right. Yeah.
Yeah.
What sort of work do you still need to do on the plane?
Well, how long have you got? The pilot had a minor engine problem, although he wasn't aware at the time how minor we now think it was. And he tried to do it. He was flying down the runway, not very high towards the end of the runway when his engine misfired. So he had no runway in front of him to land on. And he tried to do a U-turn and come back in. And he re-entered the airfield through the perimeter wall. and he took a wing off, made a fair mess of the other one and the entire nose of the plane. I knew him and his wife very well, and I was standing next to his wife. We were watching it, and we thought we'd watched him die, although in fact he survived.
Yeah.
And that he'd had the problem. From there on, he coped remarkably well. He was wandering around a couple of hours later with just an arm in a sling. But
Right.
yeah, the plane has seen better days.
That's lucky though.
We've got all the glassware sorted out. That's all tucked away, nicely wrapped up. And we've got the entire empennage, the tailplanes and all that sort of stuff in bits. And one of the interesting aspects of this kind of thing, I can get very boring here. I don't know how many thousand drawings there are of the components of Spitfires, but which versions go on which Spitfires isn't always all that obvious.
Right.
And we found a couple of aspects of the tailplanes which don't correspond with the drawings we've got. Obviously, what happens through the life of the plane?
Real numbers on
Say again, sorry?
They weren't stamping serial numbers on all the parts nice and neatly.
We wish, yeah. Yeah, obviously in a war environment, the evolution goes on all the time. As soon as they pick up something that works better or that needs fixing, they move on. There was a famous spell with the Hawker Typhoons where the tails had been coming off and the test pilots had worked out where the problem was. So for a short while, until that bit was redesigned, you will see photographs of Typhoons with little plates welded onto the fuselage rear all the way around where it tended to snap.
Improvements on the go.
And how, yeah.
Same as the Russians with the way they've been trying to armor the tops of their tanks because of those missiles that just pop straight down and hit the top of the tank.
Yeah.
So they've also been improvising very quickly on the battlefield.
Yeah. But can you imagine being the test pilot who was sent up in a Typhoon and said, put it into a dive and see if you can work out what's going on with the tail?
That's where you definitely want the simulation, hey?
Yeah. I read a book by one of the guys who used to do that kind of thing, and he said it was a slightly stressful thing to be trying.
I'm sure.
So tell me, do you sort of manufacture these parts from, I don't know, aluminium and then rivet them together, or?
It varies enormously depending on which bits you're talking about. Some of them, like undercarriage components, for example, which are not aluminium, obviously, would have to be imported. There are parts which we could fabricate ourselves. There is a whole global industry rebuilding Spitfires.
Oh.
There are some, now, can I remember what the right number? There are something like 90 known Spitfires in the world, of which something like 60 are actually in flyable condition.
Sure.
And the other 30 are being rebuilt by somebody. That is well. Yeah. But there are people, we've had contact from guys who said, give us £5 million and we'll rebuild it for you.
Oh, wow.
Yeah.
In fact, one of the jokes is if the ID of the plane is a little plate about this big, which is on the fuselage inside just near the engine. And the joke is if you have the plate for a real Spitfire, that's all you need. We will build you the rest of it.
That's impressive.
Yeah. But the odd occasions when they do change hands, when they go to auction, they're now going for up to £3 million a piece.
Yeah.
They're quite valuable.
Right, quite, yeah. Then you've got to try and find someone brave enough to fly it.
Well, yeah. Yeah.
Oh, nice.
Did you see the bit about the little old lady who had delivered them all in the Second World War? And there are a couple of two-seater Spitfires around with a second cockpit sort of behind the front one. And for her 100th birthday, they took her up in one of these. And one of the ones that she had delivered in the Second World War, literally the same plane, was in Holland, and still is, I'm sure. And they flew out over the North Sea, somewhere off East Anglia, and the other Spitfire came across and rendezvoused with them.
Oh, wow.
And flew alongside them so she could have a look, and she got to hold the control stick and everything.
That's cool.
And then they got to a point where they needed to go home, and the pilot said, okay, I'd better switch on the GPS and work out where the hell we are and see if I can find out how to get home. And she said, no need to do that. I know exactly where we are. She's doing it by the seat of her pants her whole life, and GPSs weren't anything she knew about.
Yeah.
So she could tell him exactly the route without any trouble at all.
That's amazing. Yeah.
Yeah.
Great.
Thanks very much,
Thanks so much.
folks. Excellent.
Yeah.
Well done,
Thanks a lot.
Clemens.
I'm also
Okay.
going to go, but thanks, Clemens. It was great. Thanks,
All the
Dave.
best.
Stuart. Take care, man.
See you
Okay.
guys. Yeah.
Bye-bye.
Cheers.